the quiz, turn that in today, the take-home quiz. And everybody got my correction, the typo that I made that Austin pointed out that didn't solve? Thank you for pointing that out, because otherwise I would have a problem.
I know I saw the email, but when I was doing homework, I forgot to pull it. Oh, man.
You got the what?
I got the email, but when I read it, I wasn't doing the work, and then I was doing the work, and I forgot to look at the email.
But you got the, but you couldn't solve it then, right? Okay, if you want to take like a few seconds after class to do that, that's fine.
It's impossible, like how it was written, right?
I'm sorry?
It's impossible to do, like how.
Right, with the typo, it was impossible to solve. Because you got a negative and you get it when you do the difference, right? Okay, so we're going to switch gears a little bit today. So I want to sort of spend first a few minutes on Lab 1 status, talk about that for a few seconds. Then we're going to start moving on to chromatography. And we're going to then, at the end, introduce Lab 2. So remember, 9 a.m. Monday is the Lab 1 draft to do, right? Electronically to us, to the TA, to your TA, right? To your TA, okay? If you have any questions about it, make sure you're, like I mentioned on Wednesday, to go over the guidelines and tips and the common problems and all those things that we provided to you that are on the website that I also handed out the first day. So for the data, you already know what data to include, and it's pretty clear in the guidelines, right? And I asked you for Lab 1 and for the other labs too, that on your title page, you're going to put sort of that checklist, right? Checklist on title page. And I want you to use that checklist to say, yeah, it's in here, right? Because even though it's in the guidelines, the instructions, sometimes students sort of overlook things. And so I want you to make sure that you're using that checklist to ensure that you have all those components we need so you don't unnecessarily overlook something and then end up suffering, getting fewer points as a result of that. So it's clear now, I've checked with most people during the week about their progress, and my sense is everybody has good standard curves. Everybody has been able to calculate, and to measure and to calculate the concentration of copper in the 2 unknown samples with some replication. It's true, right? I'll look for some affirmative response from everybody as I go through, right? Okay, there's no exception to this?
Sure.
Okay? Yeah. Is that true? Yes? I know it's true, because I talked to you guys yesterday, and we were making that work. And to some extent, everybody has attempted to do some type of a spike recovery experiment or method of addition experiment, right? And how many people were unsuccessful at that, meaning they feel they have absolutely nothing that they can list as some type of a number? Raise your hand if you feel you're totally unsuccessful with a spike recovery attempt. Okay? And so it's about a third of you. So if you attempted it, which I'm assuming most of you did, or all of you did, attempted it, it's okay to include in the data report your attempt and what you think went wrong. Right? The purpose of doing these kinds of experiments in the lab, in this class in particular, is not just to get the best estimate of what we think the unknown concentrations are, but it's to go through the process of sort of designing and failing in experiments and learning from that process. And with the idea that what you learn from your failures in this lab, you will transfer into the next lab to avoid those failures, not to repeat the failures. And so I think it's helpful to kind of go through that process, and this is commonly done in science, where we conduct experiments in our lab, and in our lab books, we'll record experiments that failed and why we think they failed, so that we can then utilize that experience in designing the next phase of the experiment. Okay? And so there's some benefit to it, and there are page constraints, and I want you to follow the page guidelines for this lab report closely. It's very hard in many ways to write and present things in a shorter format. It requires that you use words carefully and you be very specific and concise and all that. But that's what we want you to do. So if you are going to discuss things that you did that didn't succeed, the purpose of discussing is for you to do a critical analysis for yourself. Why didn't it succeed? One is I just didn't have time because things didn't go right and I had to redo things and blah, blah, blah. And that's legitimate because that's a planning issue, right? Or an organization issue. The other is I attempted it and it just didn't work because I made a calculation error, I did this wrong. Whatever that may be, to do some critical analysis of your failures is a very important process, right? And you don't get marked off for failures, right? Unless there's some egregious, I just didn't try or I didn't care or whatever, then it's a different story. But that's not the case with any of you. Are there any questions about any of the stuff?
Can we send you or the TA the like rough draft of it in case like the wording is off a little bit?
In case of what?
In case of the wording is off?
If you have specific questions to ask us, that's fine. If you were to bring in something physically to the TA office hours or to my office or to the lab, you can sit down and look at it. But if you send stuff to us electronically and say, can you do a pre-look at this first draft and blah, blah, give you some comments, that's probably not realistic, I think. Because otherwise people would be sending us stuff Sunday night and say, hey, look at this, before tomorrow morning and get back to me.
The TA's emails are on this course website?
You say they're not, or they are?
Or
They
I'm
are.
asking if they are.
Yes, they are.
Okay.
Yes, it should be. Yes, it should be there. Right. And know that there's no guarantee. Like I said on Wednesday, there's no guarantee if emails come through over the weekend that people will be that responsive. Right. Okay. So no other questions about any of that stuff. Okay. So so I want to switch gears. And now we're going to sort of we're jumping around the book. And now we're going to, while you're still sort of immersed in molecular spectroscopy and thinking about writing the lab up and so forth, now we're going to pull the rug out from under that and we're going to start going a different direction. And we're going to start a lab next week, lab number 2, that deals with chromatography. And so I'm going to spend today talking about sort of the basic introduction to chromatography, and then talk about it for the next couple lectures, and leave you with today sort of an overview of what to come in with on Monday or Tuesday in preparation of starting the second lab, chromatography, okay? Okay. So, these are the kind of things we're going to talk about today that I want you to sort of leave with and sort of a background. So it's just an outline that I won't go into belabor because we'll talk about those things. So chromatography is probably one of the most widely used analytical techniques in all of analytical sciences. And there's so many different permutations of it that I'll talk a little bit about. And chromatography, the word chrome, of course, means color, and graphy essentially means to write, or to so it's basically separation, talking about separation techniques that are initially used the color of compounds to detect them and to detect their separations, right? Okay. The fundamental principles of chromatography that we're going to be talking a lot about is that the goal is to separate compounds so that you can then detect them. And so when we think about chromatography, all we want to do is to separate. And then we want to have some way to detect. Okay. Now, in lab 1 with the copper concentrations in natural waters, you made no attempt to separate copper from other things, right? Some people initially proposed using the ligand like PDDC, whatever, I can't remember which one ligand people proposed. But some ligand that would bind copper and form a complex that could then be extracted into a relatively non-polar or polar solvent phase, and using a liquid extraction. And liquid extraction is sort of a form of chromatography in the sense that it is trying to separate a species based on its chemical character from one medium into another. Okay? And column chromatography is the same basic principle, but the structure of the media that has chemical functional groups that are facilitating some separation are typically different, but the basic concepts are the same. And so in this process, all we're trying to do is separate analytes so that we could then detect them with some detection system, okay? Which is different than what we attempted to do before. And in the vast majority of chromatographic systems, except for that liquid extraction system, they all typically rely on that there's two phases in which the compounds can partition. They can partition onto a stationary phase. Stationary means it's not moving. Or they can partition into a mobile phase. A mobile phase is something, of course, is moving. And it's that partitioning from one phase to the other, and the fact that different compounds or analytes partition differently to the stationary phase or the mobile phase, that allows us to separate them. And we're going to talk in great extent about that. So, when you want to learn about something and spend a minute doing it, the first thing you often do is you check out Wikipedia, and you can go to Wikipedia and look up chromatography, and you can see that there's a lot of different kinds of chromatographic processes that people have typed into Wikipedia. Right? And all of these are very commonly utilized. And so we're going to be using a column chromatography method that's based on functional groups on a stationary phase that have a quaternary ammonium ion ligated attached to it. And that quaternary ammonium, under the buffer conditions of your mobile phase that you're going to make up, which is going to be slightly acidic, that quaternary ammonium is going to have a positive charge, and it's going to allow you then to use that positive charge in that quaternary ammonium to essentially attract negatively charged anions that are flowing through in the mobile phase, and they're going to essentially transiently partition onto that stationary phase, electrostatically attract to that quaternary ammonium. And the more anionic character the analyte has, the more strongly it'll partition, and the more time it'll spend on the stationary phase. And the less anionic character, the less it will partition, and those things will flow through faster. And so you'll be able to separate things based on their anionic character, okay, based on the stationary phase. And that's an example of ion exchange chromatography that you're going to be using. So there are many different kinds of chromatography. We'll talk about some of them, but almost every lab in a research setting utilizes some form of chromatography because they're so fundamental in being able to detect constituents in samples. Okay. And these are some examples. This is out of your book, out of chapter 26, which covers all this information. And you can look across, when they classify the chromatographic methods, so the general classification might be liquid chromatography. What that refers to is the mobile phase in which the analytes are initially dissolved, that you load onto the instrument, are in some liquid form, right? It's liquid, right? Another form is gas chromatography, in which the analytes of interest are most commonly loaded onto something where they're volatilized into the vapor state, and in the gas state they're separated. Okay, that's gas chromatography. And then there's other kinds of chromatography, supercritical fluid chromatography, where they essentially just utilize the properties of the fluids to partition compounds. Right? So the most commonly used are LC liquid chromatography and to some extent gas chromatography. And if you look at the methods for liquid chromatography, you could have liquid-liquid, like that extraction method that some people had proposed in this class. Right? You can have liquid in a bonded phase. Right? You can have liquid-solid or absorption, ion exchange, site exclusion, many different variations of that. And they all come with different kinds of stationary phase. And the equilibrium that they rely upon, meaning essentially the force that's driving the partition of the analyte from one phase to the other, varies somewhat depending upon the kind of chromatography that's being conducted. And so we'll talk to some extent about all these different variations, but in particular we'll spend more time talking about ion exchange chromatography, site exclusion chromatography, and reverse phase chromatography. So I'll show this now, then I'll talk more about it near the end of Class A. This is the instrument that you're going to use. And it's a liquid chromatography Dionex 1100 IC, or for ion chromatography, the IC stands for. And it has, you know, the eluent buffer system on top, and then when you open the thing up, you see that there's, you know, a lot of little plumbing with little tubes and pumps and valves and a ion suppressor system. And then our column's going to go over here. This is the spare column. And it's basically just a very fancy pump system that pumps your solution that you're going to inject through a port in a syringe in the front, and then you're going to push a button, and then it's going to go through a program to turn a pump on, move a solenoid, pump the mobile phase, and flush out your sample through the injection loop that you just injected, and pass it over the column. And then it's going to go through, after it passes through the column, when things separate, it's going to immediately go to a detector and give some kind of a signal based on the amount of anion that's there. Okay? And the anions that you're going to be looking for are anions that are commonly found in natural waters. These would be like chloride, could be bromide, nitrate, nitrite, sulfate, sulfite. Things that are oftentimes common constituents of groundwater, particularly in areas where there's significant agricultural activities. Right? I think I mentioned last couple classes ago, there was a student who did this independent project, a pair of students, looking at bromide concentrations and runoff from agricultural fields where they think they use methyl bromide, right? Fumigant for strawberries and so forth, measured by liquid chromatography, IC liquid chromatography. And the unknowns that we're going to be giving you are unknowns that were groundwater samples were collected somewhere around some of the agricultural fields by a faculty member in the Ocean Sciences Department who does groundwater studies, looking at different kinds of anions. So you'll have a chance to look at those and characterize those. So I'll talk more about that near the end. Before I get to that, let's talk about some of the basic principles. So in most forms of liquid chromatography, as I show there, you have a column, which is essentially a tube, right? And they come in varying dimensions, sometimes really skinny, about the diameter of a pencil, maybe as long as a pencil or longer, and sometimes very, very fat, maybe about as big around as this, and they could be as much as a meter or so tall, depending on what kind of chromatography is being done. And the commonality is that they have, a cap at the end, cap at the bottom, some kind of little outlet port, some type of inlet port, and then within the column is packed the material. It's the stationary phase, and it's not moving, that has the properties that we want that are going to be facilitating the partitioning of the analytes from the mobile phase onto the stationary phase. So in this example here, we'd say I start with some column, I load a sample on top, and in this case, the sample is very simple. It has a couple constituents in it, analyte A and analyte B. I load the sample on top in some volume, I flip a switch and turn it on if it's under some pressure, or it could just feed by gravity. And as that sample migrates through the column, so at time zero we would inject it or load it on, and then over time, as the mobile phase is transited through the column, the compounds are moving through, and you see that one of them moves faster than the other. So compound A is moving faster than the other, and if we look across time, this would be elution time, the time it takes to elute the compound out of the column. So over elution time, we can see that these compounds are migrating. The further they migrate, the more they start to separate, and finally they come out, and here's the detector, down here, and compound A hits the detector first, and a peak arises at the detector, and then compound B is following that and elutes at a later time, right? And from this very simple chromatogram, you can conclude a number of things. So from the chromatogram, you can conclude what? From this simple chromatogram.
The relative percentages of A and B, like in the sample.
Okay. Yeah, so maybe. But in some cases,
Or at
yes.
least
In some cases, yes. It depends on what they look
chromatography
like.
that we do.
Let's go back up simpler than that.
There are two things.
Okay, well, there's two things there, right? Two things that I can detect. Okay, what else?
We compare the elution time to a standard, you figure out which one is which not.
Okay, we'll get to that. You'll do that in class, but that's true. So,
You can figure out like the relative ones and then like polarity. Like,
okay, it depends what kind of column it is. But even the simplest thing we can say is one, besides there's two things there, is that compound B partitions more strongly with the stationary phase than A. Right? We know that the stationary phase is facilitating some interaction, that's what they're all based on for the most part, and that because compound B came out later, right, has a longer elution time or a greater retention time, right? That compound B must be interacting with the stationary phase more strongly than does compound A, and that's why it's coming out more slowly. We'll talk a lot about that, right? So one is you can say, all right, they have different retention times or different elution times, and their different elution times tells me something about how they're interacting with the stationary phase. And depending on what my stationary phase is, which you choose as an analyst, it's going to tell you something about the character of those compounds, okay? So one is that they're partitioning more with one is partitioning more with the stationary phase than the other. Or we could say conversely that A partitions more readily in the mobile phase, right? Because it came out first, right? Than B. What else might we say in this by looking at these bands as they come through from this cartoon?
A and B proportions. Compound A has a higher concentration.
Higher concentration? No.
A might be heavier than B, that's why it goes down faster.
No.
One has a more negative charge than the other.
Okay, could. But that could relate to this, depending on what kind of column it is.
When you say it partitions more strong, I thought partition meant like split. So in this, what do you mean when you're, do I misunderstand?
And we're going to get into this. So in this case, let's say, and I'll talk about this in a minute, this is a blown up version of what a solid stationary phase might look like in this column. In many cases, the stationary phase are tiny little beads that are microscopic beads, latex beads or different constructions of different materials. And on that bead is some functionalized group. So let's say here I have an ammonia group, the quaternary ammonium, okay, which is what I think your column will have, right? Not just one, obviously, but thousands on each bead in this column's path of it. And then I'm loading through on this some anion, sulfate or whatever, chloride, whatever. And now there's going to be some electrostatic attraction between these two compounds, between the analyte and the functionalized group that's attached to the column stationary phase. And the extent of that electrostatic attraction is going to determine the extent to which this analyte is partitioned, I'd say, or associates electrostatically with that functional group. It sticks there and doesn't move. So the mobile phase is passing through, but this doesn't move there because it's electrostatically attached essentially to the quaternary ammonium. But of course, this is an equilibrium, right? It's not a covalent bond, it's an electrostatic attraction group. And so this is an equilibrium, and the partitioning is essentially represents what's the word I want? Tell me what it represents, because I'm not sure.
The constant K?
Yes.
Which side of the equilibrium?
It's a partitioning coefficient we'll talk about in a second, but I was looking for the term that I'm spacing out right now. The equilibrium is essentially reflecting the association constant, because you have, these two constituents, although this isn't dissolved, and they will form electrostatic bond, and there's going to be some kinetic process, and how stable that is and how long, based on the affinity constant, the proportion of this mixture where this is bound to this versus not, right? That's reflecting the partitioning. And so the more strongly the analyte is attracted, electrostatically attracted, and bonds with the quaternary ammonium will determine how long this stays here versus when it essentially becomes unbound, because it's this constant kinetic process of association and dissociation. And so the compounds A and B, of course, in this case, if that's B, we know from how these eluting here that B has a stronger affinity partitioning or of affinity for this quaternary ammonium in this example than does A. And so it's going to spend more time electrostatically associated with the quaternary ammonium than does A. Okay, and but it's a equilibrium, right? It's not all or nothing like a covalent bond, obviously. Right? So that's one reason why we get this, in most peaks in chromatograms, get this sort of semi-normal shaped peak, is because it reflects the equilibrium where things are kind of associated and unassociated, that process as the mobile phase is passing through. So the point I wanted to make was not that per se. The second point I wanted to make is when you look at this, the one thing you notice is that the width of the bands, based on where they start, meaning how broad they are in this column space, increases as the compounds transit through the column. And so what typically happens in almost all forms of chromatography is that there is a dilution of your analyte in the column during the chromatographic process. Meaning that it may be concentrated in the sample that you load at the top of the column, but by the time the compound elutes at the end of the column, it is in a concentration that's more dilute than it was when you first loaded it. And because it's being diluted into the mobile phase, because it has this equilibrium partitioning on and off with the functional group. And so when you look at the shape of the curve, you know, where it comes out, the vast majority of it comes out at a particular time, and if we were to put a cup here and capture this peak, what you guys won't, but in many cases people do, they want to isolate things and then collect them to analyze them for something else. If we were to put a cup here, collect it, and collect this fraction, and collect this fraction, and collect this fraction, right? The flow rate here is constant, as is in most chromatographic separations. The flow rate of the mobile phase, say 1 mil per minute, which will be what you use, or 1.2 mils per minute when you do your experiment. The flow rate is constant, so the fraction I collect here might be, you know, if I do 1 minute collection and a 1 minute collection and a 1 minute collection, they'll all be, if it's 1 mil per minute, they'll all be 1 milliliter fractions. But the concentration of my analyte in this fraction will be much less than compared to this fraction, compared to that fraction. And when I collect all three fractions in this example, 93 milliliters, and the total concentration in that 3 mils will be the sum of this peak. And that concentration will be lower, because it's been diluted, than it was when I first loaded it up. So the point is then, that for most chromatographic separations, there's a dilution of the analyte, and that reflects that there is a broadening of the peaks with elution, which is what I want to point out here. Okay, so
it's being diluted by the mobile phase?
by the mobile phase.
Okay.
That's right. By the mobile phase, it's passing through the column.
Yeah.
So you can imagine, I don't know what kind of metaphor I could use, but let's say you fall into a river. All of you guys fall into a river. We're having a flood, and the salmon runs a river, and it finally rains, and you're all walking along the river, and many of you fall in. And some of you are stronger than others, and so as you're being swept downstream, some of you are able to hold on to the rocks a little more effectively than others. And the stronger of you who hold on to those rocks more strongly will get retained in the river, and the rest of you who can't hold on at all will get flushed down with the water. The water is the mobile phase, right? And at some point, and we're waiting for you down there, PetSmart or Petco or whatever it is, there'll be a bolus of you that'll finally let go because you get too tired and you'll come down. The strong ones will come down later. It'll take you longer to finally get down there because you're hanging on to the rocks longer because you're a little bit stronger, right? And so that dilution that's occurring as you float down through, depending on your different strengths of hanging on the rocks, you guys will get spread out as you float down the river, right? It depends on how well you can hang on to the rocks, and that's the dilution that's such good. It's being diluted by the mobile phase, right?
That's it. Yeah, makes sense.
All right, so if we think of this now, the whole interaction between your analyte and what's going on at the stationary phase can be described really by a partitioning, right, like we've been talking. All right. Okay. And we can describe that with a partitioning coefficient, like all things, there's a partitioning. And in the simplest form, we can describe that partitioning looking at the concentration of your